Okay, just so I know how repetitive I need to be. How many people here have been to my previous talk at the previous TUC? Please show of hands. Okay, so barely half. So I'll repeat myself. At the risk of being repetitive, I'm Sagi from HP Labs, and I'm going to talk a little bit about what we're doing and why we're doing it, and then a little bit more about what we did with the LDBC benchmark. So HP Labs is the innovation engine for HP, has been for lots of years. When I started working in the company, my father told me he's very proud that I'm working for the company that invented the pocket calculator. He said it was the greatest invention he witnessed, so I'm proud as well. But we have done a few other things ever since. As a unit in HP, our main mission is to look beyond the 5 years into things that are going to be the major trends or major technologies in business technology. And while in each HP unit, so HP Software has their own technology unit, and HP Enterprise Group has their own technology unit, they will be looking at the next iteration of the product, the next version, the two next versions, and so on. What are the features that users are looking for? Then we would be looking at the next 5 or 10 or 20 years. What is the technology that we can utilize to make a disruptive change? We are notorious for putting HP business units out of business. Every once in a while we come up with a technology that makes some HP units start scrambling to look for their new customers, but that's fine. That's part of our charter to challenge the businesses. And as part of that challenge, we're now looking at something new that I want to talk with you about. Just putting me in, HP Labs is a big organization. We have 5 labs. It's called HP Labs because we have 5 different labs. I'm part of the analytics lab, which focuses on data analysis, data management. And half of the analytics lab is located in Israel, which is where I'm from. This is us. I'm not there, so don't try looking for me. It was taking a couple of months before I joined. But if I would be there, I would somewhere in the middle of the bottom by size. Now, what we're currently working on at HP Labs, a lot of us are working on something called the machine. The machine is based upon a premise that the current technology for managing data is coming to an end, an evolutionary end, that it needs to go through a revolution before it can continue. The reason is that the pace of compute power that we are experiencing is not matching the pace of compute needs from the explosion of information and big data analysis that we can see these days. If you take the current trends in data analysis and data generation by the human race, and you superimpose them upon the current trends in power and compute capabilities, you see that in a couple of years we're going to need more planets to store our data centers than we currently have. And so the question is, what do we do? And the answer is that we're looking at a new paradigm. The current PC is based upon, or the current computer, whether it's a PC or a server, is based upon a paradigm that was invented somewhere very far along, and all of the computers look the same. You have a processor and you have a memory on board, and then you have some type of a storage device that is magnetic or flash or whatever, and they're all connected together with copper wires. And the farther you go, the hotter things get, so you also need a fan to cool everything down. So we're here to suggest something new, or here we're to use something new. We're calling it the machine. The machine is based upon 3 components. You have a sea of cores, a sea of compute resources sitting somewhere, and you have a collection of memory pools, of memory units called memristors, if somebody heard the name. It's a new type of memory that is both non-volatile and speedy. And these are connected together with photonics. So instead of transferring data over copper wires, we'll be transferring data over photons within the machine. Now, this idea was a very nice idea, but the question is, how does it work? And that's where we come into place. First of all, the idea is that if this is a very big data center and it's all combined of machines, it's all constructed of machines, then a single CPU socket here is able to access a piece of information sitting here at pretty much the same latency as it would in a normal computer, in a single unit computer. And which causes something, which creates some dilemma within the memory hierarchy. Are we still taking things from storage, copying them into the DRAM, then creating a complex computation between the DRAM and the CPU, or can we do something else? Skip this. So, what we were told as HP Labs is that this new compute paradigm changes everything. You don't have to go through DRAM anymore. You can compute things directly from the storage, the persistence. You don't have to do serialization and I/O and everything, because everything is all the time is persistent. But the question is, does it change everything? Do we really need to change the ways we write programs? Do we really need to change the way we run queries against databases? Do we really need to change the way we optimize queries? And if we do, how? So our research agenda is to look how does this new change in computer power and computer architecture change the way that data analytics works, and my specific charter is to look at the graph databases and how they are impacted. So, what are we doing here? We took the LDBC as the most forward-looking benchmark in graph technologies, and we jumped on the wagon, and now we're trying to use it in order to check how does a balanced read-write workload look on this new technology called the machine. If we have non-volatile memory, how does a graph query optimization look like? Because maybe you don't want to do the same things you did in relational databases or in graph databases on hardware, on hard disks. Maybe you want to do something new. The current split is that you have a relational or some very fast transactional database supporting OLTP, and you have some in-memory huge machine that has very fast, very low latency to do the OLAP. The question is this split avoidable? Can we use a single implementation, a single machine, and support both rapid interactive transactional style queries and cross-data analytics style huge queries like give me user clusters and so on? And finally, can we use a graph database? We chose Titan for, not for performance reasons, I must say, to look at this issue, but can we use a graph database, no matter which one, to support both OLAP and OLTP? And finally, how do we compare our performance? Are we looking at the same things with SSDs, with in-memory databases? Are we somewhere in between? Are we better than both? These are some things that we wanted to look at. So, I can't show you much. It was very hard to put these slides together because most of the things I wanted to tell you I cannot tell you due to proprietary reasons and patents and so on. Sorry, Hassan. And so what I could say is this. If we take the kind of raw latency and throughput numbers for the 4 technologies that we're looking at for memory management, we get something like this. This is a logarithmic scale graph, and you can see that NVRAM technology, memory store technology, is going to be somewhere between DRAM and SSD. If you believe the marketing, it's going to surpass DRAM sometime in the near future, but first release will probably be somewhere here. And the question is, what does this do to query performance? So to examine this question, we took one of LDBC's queries, query 2, for example, and query 2 is simplified to be this one. If you have a root person and a date, you return all of the posts that person's friends created before a given date. So naively, a double expansion plan would be get all of that person's friends, and then for each of one of these friends get all of their posts, and then for these posts take those that were created before a given date. Of course, you can go the other way around. You can take all of the posts from a given date and check out which were written from this person's friends. So kind of simplify, you have 3 basic query plans you could write. The first one is the double expansion. friends, posts, relevant posts, and then the content of those posts. Second one is a bidirectional search. Go from the friends on one side, from the relevant posts on the other side. It's a meet in the middle. And the third is use a very big index that has every ID and date indexed, so that you can just efficiently get only those posts. There you're paying with memory for latency. So if we take these three query models and we run them against theoretical machines, again, these are theoretical numbers because we don't really have working NVRAM yet. We're supposed to have it sometime 2016, but right now this is what we have. We see interesting phenomenon. Now, of course, when you go from HD, from hard disk, spinning disk to SSDs, you go faster. You go 2 orders of magnitude faster. And of course, if you move from SSDs to NVRAM, you also go 2 orders of magnitude faster. But something interesting happens. You can see that on the bidirectional search, using SSDs, it was faster than the double expansion. But when I'm using NVRAM, the ordering of the performance changes. Now, the question was, why did this happen? And we looked into it and we saw that when I'm running this on NVRAM, the compute time, so the time it takes me to intersect the results from the bidirectional search, you need to intersect these posts with these friends posts, and then to get the result. So the intersection time in the main memory using the CPUs was taking up most of the time of the query. And so if in traditional query optimization we would neglect the CPU time in the computation of the runtime, or at least not take it as one of the more influential components of the computation, then when we're looking at NVRAM technology, we need to start thinking efficiently about compute, because sometimes streaming out of the I/O, out of the persistence, large amounts of data can be faster than computing small amounts of data in the CPU DRAM combination. So this is a new way of thinking, because we need to rethink our query optimization models. Do we use the existing cost models? Do we change the weights and that will be enough, or do we need new models? It certainly goes against things that I have taught myself in database management 101 in the university. So we need to rethink these things. And now that we have the LDBC, we're looking at these types of behaviors on different types of queries, on long traversals, on short queries, on big queries, and so on. We want to see where are the places that the compute paradigm really changes when we introduce NVRAM. So what are we doing for LDBC? First of all, it took us 6.5 months to get corporate approval to contribute to the LDBC. I think we broke an HP record for approval processes. It was really amazing, but we finally have confirmation. We can now contribute to the LDBC. So we have contributed our implementation in Gremlin. If somebody wants to look at Gremlin queries for LDBC, is welcome to look at our implementation and change it, of course, if you want. And we hopefully, as soon as the BI workload is released, we're going to contribute an implementation for that as well. We're helping kind of tweak the documentation and give some back with the query validation tools. We have a nice tool that, let me just, we have a nice tool that can compare the actual and expected results in a table form and show exactly why the query failed validation, if it was a missing attribute or a different sort order and so on. We gave that to the LDBC repository. And since the technology we're using is very much still being written in C and assembly and C++, then we're going to try and port the LDBC driver to C++, see if we can manage that. It's a resource issue, but we hope we can get over that. We ran the interactive workload on Titan. We used one of our machines, our research machines, DL380, with 32 gigabytes given to the Java heap, 24 cores, a very good hard disk. And Titan 0.5.1 was used, a Berkeley DB backend. Thanks, Oracle. And Well, we ran scale factor 1. This is the results that you see. We also ran 3, 10, and 30. They all run. We only ran the long reads because the short updates, the short reads are just finished. They're not really finished. Every time I get a ping by Alex, and now that things have changed again, and I have to rewrite my implementation. So it's really a moving target, but we're trying to keep up. Now the performance is not stellar. You can see query 9 here. The median is a 54,000 milliseconds. That it, right? Which is really bad. The choke points work well. It's really choking. Now, interesting thing that we saw is that the write load, the write operations were not challenging the database at all. I mean, we had the settings wrong and we had it very time compressed, so it was the driver issued all of the queries at the same time to the database, and the database in 1 second completed all of the write queries and then started grinding through the read operations. So we had I think it was 90,000 operations per millisecond on the write queries, and then the rest was like, okay, 2 seconds per query and so on. So we need to look into that. It seems like the write load is not very heavy, but maybe that's indicative of their real-life workloads as well. It's anybody's guess.
Scale factor for these diagrams?
It's 1. Scale factor 1. Yeah, it's really horrible performance. I'm sorry. But then again, we're looking at Titan as a research vehicle. I mean, we were more interested to see what happens in this diagrams when we switch from NVRAM, from SSD to NVRAM and back, and when we apply different query optimizations that are dedicated to NVRAM, then we are interested in having it beat. I don't know who's the other, Neo4j. We're happy to give Neo4j the lead for now, since HP Labs is not a database vendor. Then we don't really aiming for performance. Yeah.
So Titan is, at least the way I understand it, just a layer really on top of the real thing that you're testing probably, which is the Berkeley DB on top. You know, that's what's being exercised, right? So
Yeah.
do you have a plan to explore maybe other backends, or maybe?
Yeah, we're in the process of replacing the backend. Well, Titan is it was chosen because it's very tinkerable. You can open it up and replace stuff. We replaced the backend with MapDB, and the reason we did that is because MapDB has is also tinkerable, and one of the things is that it has a persistence volume class that is replaceable as well. So you can take the persistence layer and replace that. So we're replacing the persistence layer with an NVRAM simulated persistence layer. And when we have that, then we can compare NVRAM versus file-based persistence versus main memory, in-memory databases. So that's our aim. The first run was with Berkeley DB just to see how it works, but yeah, that's where we're going. We're also trying Cumulo as a backend, but and that's for there's another project in our lab. It's called Spark for the Machine, and they're trying to do a Hadoop Spark stack that works on the machine, and so we're using a Cumulo to see how that works.
Yeah, to clarify on those read queries that are very slow.
Mm-hmm.
So there are kind of two kinds of read queries in the interactive benchmark. So there are the ones that are slow are probably the heavy read queries.
Yeah.
But there is also, for every heavy read query, there is a number of short read queries which is supposed to be executed, I think.
Yeah, I just finished the implementation of the short reads last night at 11 p.m. on the plane.
The short read should be faster and should give you a better feeling about the system. But yeah, the heavy reads will remain slow, probably.
Well, actually, the heavy reads are more interesting because they allow us to really compare the optimization technologies.
That's where the choking is happening.
Yeah, so we're happy about it. But yeah, next time we publish results, we'll give you the full spectrum.
I'm sure that if you talk with Arnau and Moritz, they have been working these last days on this. I'm pretty sure that Alex also has been involved in that, so you'll probably get feedback from them so that you can...
Oh yeah, me and Alex are connected.
Yeah, I know. But
Okay, thanks, Domen. With that, it's time for
Lunch.
thank you.